Bismillahir Rahmanir Rahim. Dear students, today we are going to discuss another reaction about the formation of carbon nitrogen bond, and this is the last reaction of this type of bond reaction in our syllabus. UG reaction is basically about the synthesis of amides. During this reaction there is creation of two carbon nitrogen bonds. One nitrogen is attached with two carbons of different moieties. This reaction involves four components for the synthesis of the final product, and these four components include the use of amine and amine, number 1, number 2 aldehyde or ketone, number 3 isocyanate, and number 4 a carboxylic acid. So all of these four components are mixed with each other, and this is one part synthesis, and we get the final product of amides. The main features of today's lecture, as you can see, the key points of today's lecture are introduction to UG reaction, the overall mechanism, the stepwise explanation of the mechanism, some general features of UG reaction, some modifications of UG reaction, and then different synthetic applications of this reaction in the medicinal field and also in general chemistry. Here we talk about our main lecture, that is UG reaction. It was first reported in 1959 by UG, and that combination of isocyanates in undergo a four component reaction in the presence of amine, aldehydes or ketones, and carboxylic acids, and we get a single condensation product of these four components. And today this transformation is now known as UG 4 component reaction, U4CR. Here you can see the general overall reaction of this UG reaction, that a carboxylic acid bearing R1 moiety, then amine R2 moiety, then ketone or aldehyde bearing R3,4, and then isocyanate bearing R5 moiety, combined with the removal of a single water molecule, we get the final product. This is basically amide, and here you can see the different color combination will tell you about the different parts of this molecule. Here you can see the R1 and carbonyl, that is a acyl moiety which is combined with amine. Acyl moiety has come from the carboxylic acid functionality. Then the R2N amine moiety is present here, and you can see there is formation of two carbon nitrogen bond of this amine. Nitrogen of this amine is bonded with acyl group which has come from carboxylic acid, and also with the carbon of aldehyde or ketone functionality. So these two carbon nitrogen bonds are newly formed bonds. Therefore this reaction is kept under the heading of carbon nitrogen bond formation. Then the at third position is the carbon in green color, which is from aldehyde or ketone moiety, and then there is the carbon, nitrogen and R5 group from the isocyanide moiety. So combination of these also termed as we named it as this first R5 NH and carbonyl is termed as carboxamide, and this carbon bearing R3 R4 is termed as alpha carbon of this carboxamide moiety. And then nitrogen, amine, and next is the acyl group. So we term as alpha amine, this aldehyde carbon, aldehydic carbon या ketonic carbon is termed as here alpha. So it is alpha substituted with acyl amino, alpha acyl amino carboxamide. So overall this molecule named as this. So this is the overall reaction of Ugi 4 component synthesis, in which 4 components has been combined together to form a single moiety with the removal of single water molecule. And also due to high reactivity of isocyanides and this reacting species, we do not need to use a catalyst for the propagation of this reaction. This is the overall mechanism of this reaction, Ugi reaction, that this mechanism is given with the basic carboxylic acid. First, aldehyde, here is shown as aldehyde, is interacting with the amine, and we get the imine after the removal of water. This imine interacts with the carboxylic acid and is got protonated by it, and after this protonation, the isocyanide acting as a nucleophile attacks on this moiety, protonated imine moiety, and then we get an addition product of both these reactants. In the next step, another molecule of carboxylic acid or the previously byproduct of carboxylate ion can also be used here, and a pure molecule, another molecule of carboxylic acid can also be used here. Here is another molecule shown here. It interacts as a nucleophile through its carbonyl oxygen and attacks on the carbon of isocyanide moiety, and we get the final addition product with which after the cyclization, that is the amine, lone pair of amine acting as a nucleophile attacks on the carbonyl of this acid functionality, and we get a 5-membered cyclic ring. And this 5-membered cyclic ring, after some bond formation, that is, there is a double bond formation between carbon and oxygen, and the oxygen carbon bond is broken, which moves towards the isocyanide carbon, making their double carbon oxygen double bond, and carbon nitrogen double bond of isocyanide moiety has been removed into a single bond, and we get the final product after this acyl transfer from the carbon of isocyanide moiety to the nitrogen of amine, and we get the alpha acyl amino carboxamide product. This last transferring is a specific rearrangement which is also known as mum rearrangement. Here is the stepwise mechanism of this Ugi reaction. First is the step is about the imine formation. In imine formation, aldehyde molecule is treated here with an amine. The nucleophilic nitrogen of amine attacks on the carbonyl carbon with electrophilic character, and the carbon oxygen double bond is converted into single bond, along with the formation of alk oxide anion, negative charge on oxygen and positive charge on nitrogen because of 4 bond formation. In the next step, this oxide anion gets the proton from this ammonium functionality, and the nitrogen hydrogen single bond move towards the nitrogen, making it making it a trivalent nitrogen instead of tetravalent. So the positive charge on nitrogen is finished, and the oxygen after protonation is converted into OH group. As we know, oxygen has 2 lone pair, and these lone pair acting as a nucleophile attacks on the neighboring that is vicinal proton, which is attached to nitrogen, and due to electronegative nitrogen it is also partial positive charge. This lone pair attacks on this hydrogen, and the nitrogen hydrogen bond moves towards the carbon nitrogen bond, making it double bond, and the carbon or OH bond has been broken due to the formation of water molecule, and after the removal of water we get the imine formation. Here can be a question that oxygen, we know there are two lone pairs on the oxygen, but at the same time we have nitrogen which has one lone pair, and we know that nitrogen is strong nucleophile as compared to that of oxygen. So there should be an attack from this nitrogen on the proton which is attached to the oxygen, and if this happens, then we shall move towards the reactant side, that is the previous side in which nitrogen was making 4 bond with positive charge and oxygen was with negative charge. So in actual practice all these steps are move in reversible manner, but we are showing this step because it leads us to the formation of imine formation. In the second step, reaction of imine with acid and isocyanides. Imine is now treated with the carboxylic acid and is protonated. The lone pair of nitrogen of this imine moiety attacks on the hydrogen of carboxylic acid functionality, and oxygen gets the negative charge. So we get the product in which nitrogen is protonated and is written with positive charge due to 4 bond formation, and this positive charge is counterbalanced by the negative charge of carboxylate anion. This carboxylate anion remains there, but now the isocyanide functionality attacks through its nitrogen through its carbon, acting as a nucleophile on the carbon which is attached to this double bonded nitrogen. So this carbon double bond nitrogen moiety is acting as like that of a carbonyl functionality, in which carbon is a bare electrophilic character, and so this due to this electrophilic character, this carbon nucleophilic carbon of isocyanide can attack on this carbon, and we get the product in which now isocyanide functionality has attached to this carbon, and the carbon nitrogen double bond has been converted into single bond. But here you can see in the product side the nitrogen of isocyanide functionality is still with positive charge, and this positive charge is counterbalanced by the carboxylate anion. And this carboxylate ion then acting as a nucleophile attacks on this carbon of this isocyanide functionality, and this carbon is electrophilic due to triple bond with nitrogen, and the triple bond of nitrogen is converted into double bond, and we get a simple uncharged molecule species. Here a very important question, that in this first step after the formation in step 2 of reaction of amine with acid and isocyanide, when first imine reacted with carboxylic acid, and we get the protonated imine along with the carboxylate anion, and now isocyanide acting as a nucleophile attacks on the carbon which is double bonded with nitrogen. The question is that we have two nucleophile here. One is carbon of the isocyanide functionality, and other is the oxygen of this carboxylate anion, which is balancing the positively charged nitrogen, this imine protonated imine moiety. So why the nucleophilic attack is through carbon of isocyanide and not through the oxygen of carboxylate ion? Because the nucleophilic character of carbon here carbon is greater as compared to that of oxygen. It can be explained in this sense also. Carbon, you know that carbon belongs to 4th group and oxygen belongs to 6th group. Due to small size, number one reason which can be here, due to small size of oxygen as compared to that of carbon is more nucleophilic. One thing. Second thing which can also be shown here, and should be discussed here, which is a basic chemistry also. That carbon monoxide molecule acts as a lone pair, or you can act as a ligand in the organometallic chemistry. And in that case, if you see the bond formation of this carbonyl moiety with the metal, transition metal, is through carbon, not that of oxygen. Although oxygen, in case of carbon monoxide molecule, in case of the oxygen has two lone pair and carbon has one lone pair. But if we draw the MOT diagram, then you know that carbon is less electronegative or more electropositive as compared to oxygen. So in the energy level, carbon is somehow at a higher position as compared to that of oxygen, and oxygen, due to high electronegativity, bears less energy as compared to that of carbon. So due to high energy level of carbon, the HOMO of this species will have more character from the carbon. So the HOMO lone pair in the HOMO highest occupied molecular orbital acting as a nucleophile will be from the carbon side. Same case is here. In case of carbon, it has less electronegativity, so its HOMO will be at higher position as compared to that of carboxylate anion, and so the higher HOMO at higher position is more energetically more active, more favorable for the nucleophilic attack. Here is the last step of this UG reaction, that is the formation of the final product alpha acyl amino carboxamide. Here you can see the previously synthesized neutral species, which is now moving in such a way that the acyl group is shifted towards the nitrogen from this oxygen, and we get the final product. This shifting moves in such a way that first the nitrogen, single bonded nitrogen, that is sp3 hybridized nitrogen bearing one lone pair, attacks on the carbon of the neighboring acyl group, which is electrophilic in character, and oxygen is converted into alkoxide ion. Here can be a question that why the nitrogen of the imine functionality, there is R3 and double bond C functionality. The nitrogen, this nitrogen which is double bonded with carbon and is attached with R3 group, is sp2 hybridized, and the nitrogen which is now attacking on the carbonyl carbon is sp3 hybridized. And as we know, if we compare this sp3 hybridized and sp2 hybridized nitrogen, then we come to the conclusion that the sp3 hybridized nitrogen is more nucleophilic as compared to that of sp2 hybridized. The reason can be explained in such a way that in case of sp3 there is less s character, so the orbitals of this nitrogen are not closer to the nitrogen of the nucleus of the nitrogen, and so the lone pair will be more easy for the nucleophilic attack. But in case of sp2 hybridized, due to large s character, the orbital contain are near to the nucleus of the nitrogen due to high s character. So therefore the lone pair has nucleophilic character, but it is less as compared to that of sp3 hybridized nitrogen. So in first step, nitrogen of sp3 hybrid attacks on the carbonyl carbon of acetate, and we get the 5-membered intermediate. Here two possibilities can be. First possibility is shown here, that for the imine nitrogen of imine functionality bearing lone pair attacks as a nucleophile and attacks on this hydrogen which is attached to this positively charged nitrogen. How is possible for such a long distance attack? Because you know this 5-membered ring is a saturated ring, and due to saturated there will be much structural bending, and so it is stereochemically approachable proton by this lone pair. So therefore this attack is possible, and if this attack happens, then the imine nitrogen is protonated with positive charge, and now the oxygen, negative charge oxygen, moves towards the carbon, making their double bond, and carbon oxygen bond has been broken, which moves towards the next carbon oxygen functionality, which is now converted into double bond, and at the same time carbon nitrogen double bond is shifted into single bond, and positive charge of nitrogen has finished, and we get the final product. This thing can happen another way, that instead of attack from the lone pair of imine functionality to the proton, the alkoxide ion can also attack as a nucleophile on this proton, and it is near to this proton as compared to that of nitrogen of imine functionality. So if attack is from alkoxide anion, then we get the OH group formation, and in the next step, with the similar case, nitrogen attacks on the lone pair of nitrogen of imine functionality attacks on the hydrogen of this OH group, and the oxygen hydrogen bond, 2 electron moves towards the carbon oxygen bond, making their double bond, and at the same time carbon oxygen bond is broken, and next carbon oxygen bond is formation, along with the single bond formation between carbon and nitrogen, and we get the final product of acyl shifting. This MUM rearrangement has also been summarized with a journal example here, that here you can see imine functionality, which is bearing acetate group here on its carbon, and now through the attack of this imine functionality, the acyl group is shifting towards the nitrogen, and the carbon is converting it to carbon oxygen double bond. So this acyl shifting is termed as MUM rearrangement. So this is the overall step by step discussion of this mechanism, and thanks. Here are some general features of this UG reaction. First, it is very easy to carry out. Usually the isocyanide is added to a stirring and well cooled solution of other three components. That is, as we have discussed in the mechanism also, first amine and aldehydes are mixed ketones are mixed together, then carboxylate ion is added for protonation, and then isocyanide is added for the formation of the product. So it is easy and fast reaction. Second, in case of less reactive aldehydes or ketones, it is advisable to pre-condense carbonyl compound and amine to form the imine. First, amines and aldehydes and ketones are mixed together to form imine, and then the other reactants are added. As the reaction is very exothermic, so adequate cooling is necessary, and so most of the time this reaction is happening at 0 degree C or some negative temperature, and the reaction typically is carried out between -80 degree C to 80 degree C, and it may take a few minutes to a week to go to completion. This time variation because of the depending upon the nature of the moieties present in these functionalities, which may enhance or which may decrement the rate of the reaction. The high concentration 0.5 molar to 2 molar of reactants give the highest yield. Polar aprotic solvents like DMF also work well, but the protic solvent can also be used like methanol, ethanol. This is a N-catalyzed reaction and also very high atom economy. A very high atom economy means if 3 atoms of one molecule and 2 atoms of second molecule are combined together, we get the 5 molecule of the product, then that is the percentage yield is high, will be high, and there is too much less loss of any atom or any species. Here in the case of UG reaction, you have seen that only one water molecule was eliminated after the combination of these 4 components, and we get the final product. So therefore there is a high atom economy, less loss of the atoms as a byproduct, and so therefore its yield is also too much high. The last slide we have discussed about the general methodology which should be adopted for the progress of the reaction, and here are something about the nature of the reacting species. First, amine component can be any compound with a sufficiently nucleophilic NH group, like ammonia, primary and secondary amine, hydrazine and its derivatives, diaziridines or hydroxyl amines. All can be used because all of them have strong nucleophilic character of their nitrogen atoms. The diaryl amines are usually not nucleophilic enough to react, so therefore they are recommended not to be used, with the exception of diaryl ketone. The diaryl ketone also are recommended not to be used because of the steric hindrance of these large groups. There is less reaction efficiency. Almost all aldehydes can be used, and also the other ketones can also be used for this type of reaction. A wide range of carbon isocyanides undergo this transformation. When nonpolar solvents are used for or the reacting components are bulky, the Pessirini reaction. Pessirini reaction is you can say is a reaction which moves along with the UG reaction, because UG uses 4 components, that is amine, aldehyde or ketone, second and third carboxylic acid, and fourth one is isocyanide. But the Pessirini reaction does not use the amine functionality. It uses 3 components only. So therefore there can be side reaction which resulted into the formation of alpha acyloxy carboxamides due to absence of amine. If amine as a UG reaction uses amine, so we get alpha acyloxy amine carboxamide, but in Pessirini reaction there is not used amine, so therefore we get alpha acyloxy carboxamide, and this can be a side reaction along with the UG reaction. Here is some modification of UG reaction which is known as UG Diels adder reaction. Modification is termed in this sense that first this reaction moves in 2 steps. First step is the basic UG reaction, in which isocyanide and aldehyde, amine and carboxylic acid, all the 4 moieties interact with each other and form a product which is the basic UG reaction product. But then in the second step, here you can see the first step on the after reaction. Here you can see at the bottom, on left side of the bottom, there is the product which is basic UG reaction product. But then it moves through the Diels adder cyclization process, in which a diene and a monoene interacts with each other, and we get a cyclization product or cyclized product. So therefore this type of reaction is termed as UG Diels adder reaction. The second modification is termed as UG Smiles reaction, in which the first step is just similar to the UG reaction, that 4 components are interacting with each other and we get the UG product. But in the second step there is a simple rearrangement like that of mum rearrangement, that here is the aromatic system is shifted from this oxygen to the nitrogen, and we get the final product here, and this oxygen of imine moiety is converted into C double bond O, and the nitrogen from amine is directly now attached to the aromatic system, and so therefore this termed as smile. This rearrangement is termed as smile rearrangement, and so overall we term this reaction as Ugi smile reaction. This rearrangement can be explained in such a way that here you can see the lone pair of this nitrogen of amine attacks on the carbon through a nucleophilic attack on which of the benzene ring, and the heterocyclic double bond moves towards the nitrogen, and then the nitrogen moves back towards the system, making double bond, and now carbon oxygen bond is broken and new nitrogen carbon bond has been formed, and we get the product with 96% yield. The next modification is termed as Ugi Buchwald Hartwig reaction. This reaction also includes the similar first step, that is the formation of Ugi product, and the second step is the formation of a cyclic ring, 5-membered cyclic ring, and this is due to the presence of halo group on the aromatic system. And this halo group, like here you can see the iodine is present. This iodine goes through condensation reaction with the neighboring amide, nitrogen of amide functionality, and we get the cyclized 5-membered ring after the removal of Hi group from this moiety. The different regions used for this purpose were organometallic compound of palladium, then base potassium carbonate, toluene, and acrylonitrile as a solvent, and then methyl cyanide as a solvent, or ethane nitrile, you can say it is also termed as acetonitrile, is used as a solvent. In 180 watt mean this reaction was progressed under microwave oven at 180 watt 100 degrees C temperature, and also with the methyl phosphine as a this structure of methyl phosphine is also shown here, Me-phos. Here is the last modification of this reaction, which is termed as Ugi-Heck reaction. The first, here you can see the product, which is the reacting species are here similar to that used for the Ugi reaction, that is amine, isocyanate, aldehyde, and then carboxylic acid. And if you see the product, then the main the change from the Ugi product is that here you can see the hydrogen with a green color, that is aromatic system bond of this benzene ring is and at the same time you can see another green color bond of iodine in the carboxylic acid moiety in the reactant side. So after the formation of the Ugi product, the next step was the removal of this Hi a molecule from the species from the product of Ugi reaction, and then we get this cyclized product. This also uses some other reagents like methanol, room temperature, organometallic as a catalyst, potassium carbonate base, DPPF it's a ligand हो गया, and ligand sometimes ligands are used along with you can see palladium diacetate is a salt, and now DPPF is acting as a ligand for the catalytic pathway, and then N-butyl ammonium bromide also acting as a base, DMF solvent, and 80 degrees C temperature is used for this reaction. Also this DPPF ligand, we have also used this, mentioned this in some previous lectures. This is the abbreviation of bis diphenyl phosphinoferrocene, and structure, I think its structure was also given in the previous lecture. Here are some synthetic applications for this Ugi reaction. Here you can see the first reaction in which an aldehyde, here is methyl you can see acetaldehyde. And second is an heterocyclic amine. Third is heteros carboxylic acid, bearing in which NH group is also present, which is has been protected by Bock protecting group. If you remember the Bock protecting group, it was the tertiary butyloxy carbonyl protecting group. It is an ester which is used as a protecting group. And the fourth one is the aromatic isocyanate, and all of the four acting species were reflexed with 95% yield, and we get this intermediate which is pure UG reaction product, and then after a number of steps we get the final drug, which is an anti-tumor drug. The second example is racemic amino acid, which interacts with an aromatic aldehyde, and then on reaction with cyclohexyl isocyanate we get the final product. And due to presence of acid and amine moiety on the same ring, we get a cyclized product, which after some rearrangement is converted into a another cyclized 4-membered cyclized ring. This you can say this 6 1 2 3 4 5 6 7, this 7-membered ring has been converted into 4-membered ring after the removal of some part of this molecule. You can say it is simply removal. I think it should not be said as removal, because it is a simple rearrangement. That amino group, NH amino group, is now attached to the carbonyl, and the C double bond N moiety is now converted into amide functionality. That is, there is simple rearrangement and we get this final product. Here is some other example of this application of this reaction. First is the moiety in which a tricarboxylic acid benzene aromatic system having 3 carboxylic acid moieties functionalities has been used, and you can see the similar type of reaction has occurred on the 3 carboxylic acid moieties, and we get a single molecule in which all the 3 carboxyl groups of aromatic benzene ring has been occupied and has moved through the UG reaction. The next reaction is about the formation of UG reaction, but this in this reaction you can see we are using diamine, number 1. Number 2, aldehyde and carboxylic acids are present in the same ring, and third is the isocyanate. In the methanol and room temperature, the product has been achieved in this way, as we are bearing diamine, so 2 molecules have been used of this aldehyde bearing benzoic acid functionality, and 1 of isocyanate functionality, and we get the final product is a cyclized product here. Here the different variable R1 and R2 are also listed here. R1 can be alkyl and benzyl, and R2 can be hydrogen, chlorine, or phenyl, carbonyl, or you can say benzoyl moiety, and benzo fused rings can also be used here. Here you can see the drug Pfizer, which has been also in using this UG reaction pathway. Here you can see the 4 reactants. One is aldehyde, second carboxylic acid, third is isocyanate, and fourth one is the amine, and all of them are reacted to form the product, which after hydrolysis with HCl we get the final amide, in which now the amide N substitution on this amide functionality has been removed, which is now shown in red color, and we get the final drug. Here is the second drug molecule, which is termed as GSK, and this drug also uses four similar functionalities: aldehyde, carboxylic acid, amine, and isocyanate. And using the UG reaction pathway, the molecule is synthesized with absolute deprotection and cyclization. Deprotection from this POC species, and then cyclization we get the final diketopiperazine moiety, and this is the final drug which is used in the medicinal field. Another drug which is used in the medicinal chemistry, or you can see in the field of medicine, also uses the this UG reaction pathway: aldehyde, acetaldehyde, along with amine, isocyanate, and carboxylic acid are interacting with each other, and you can see the formation of the UG product, but with 90% yield. And then UG product, after a number of steps, has been converted into the drug molecule, which is termed as actinosidine 743. There were a lot of examples for this UG reaction, but I have summarized these reactions into some specific which are basically related to the drug molecules. And so this is the last example for this UG reaction. The drug bicyclomycin has been synthesized after a number of steps, and one of the step involves the UG product formation, which has been formed from a carboxylic acid, amine, aldehyde, and isocyanate. Four functionalities are treated with the removal of water. We get the final UG product, which after a number of steps has been converted into this bicyclomycin product. So this is all about of the UG reaction, synthetic applications, and some general features. And thanks.